let's get started with the next session. So the first speaker is Thomas Grimm.
Thanks a lot. First of all, I would like to say my thanks to the organizers of this conference, which I enjoyed very much so far. And I would also like to thank them for giving me the opportunity to speak here. So what will I talk about in this talk is some recent progress we made by applying ideas from tame geometry and the resulting theory of complexity to QFTs and the landscape. And I was asked to focus mostly on the landscape applications. I've done this in a couple of works, and I highlighted here my junior collaborators, my two current PhD students, and my two former PhD students. Let me start with some introduction. So we begin with the quantum field theory. I sketched one here. Imagine that you have a number of scalar fields phi. They might have a non-trivial matrix K and a scalar potential V. And we want to understand if we can investigate some of the properties of such a QFT, for example, the vacuum structure of such a QFT, by using a measure of complexity associated to such a QFT and its observables. In order to do that, it means I have to tell you what sort of complexity I'm using, and the suggestion is that we use something which is called geometric or maybe logical complexity, which arises within the field of tame geometry. This is really a notion of complexity which is assigned to a function or a set. And if you want to have a rough feeling for what it means, it counts the amount of information you need to specify to encode the function or the set. Now, if we apply this notion to a generic QFT, which you might imagine, it turns out that this complexity is very quickly infinite. For example, imagine that your scalar potential is a generic analytic function which has infinitely many coefficients which have no algebraic relations, and then you would find that this is infinite. Other examples where you see that this complexity is infinite, but it's in somewhat more subtle reason, are potentials which have infinitely many vacua, or even such accumulation points like in this case. Now, how can we proceed? Well, either we can pick a very specific QFT, which is sufficiently nice, or we focus on the set of quantum field theory, effective field theories, which arise in string theory. We actually expect these to have better finiteness properties, and I give you two arguments here. The first one is that, of course, string theory has no free continuous parameters, and all the effective couplings in the effective theory are therefore determined just by fields and, very importantly, discrete choices. Okay? So we expect maybe a somewhat nicer behavior. Furthermore, starting as early as in 2005, there have been finiteness conjectures, namely about the finiteness of effective theories which arise from string theory, and this is now a central part of the swampland program. So what is the unifying perspective which I'm proposing in this talk? I propose that instead of merely focusing on finiteness, we actually should focus on a generalized finiteness principle, which I explain is stronger, namely tameness, which is induced by what is called o-minimal structures. Furthermore, I'm suggesting that we should use geometric complexity, this notion which I mentioned before, which is now very recently defined via what is called sharp o-minimality, to give a quantitative measure within a single QFT or on the space of QFTs. So you can imagine that this is a way, in order to a chance to do this, this must be a very broad framework, and in fact it is. Okay? Nevertheless, I want to start as simple as possible to give you an idea of what this really means. Let's think about the complexity of a polynomial. There is a natural way of thinking about the complexity of a polynomial by just asking what is its degree d or the number of variables f. Okay? Roughly speaking, this gives you the amount of information, namely the amount of real coefficients you have to specify. But this complexity also can be used to bound, say, the number of zeros of this potential. It also can be used to bound the volume of such a polynomial. In fact, if you put a box of radius, a ball of radius r around it, its volume will be bounded by this complexity here, this function c here. Essentially, intuitively, if you want to squeeze into a unit ball a very complicated a polynomial of high volume, you need to make it very complex going up and down. Furthermore, you can also estimate the number of epsilon balls which are needed to cover this set. Okay? The question is now, how do we generalize this to more general functions which we need in physics? First example, we certainly need the exponential function. Okay? Exponential function is the sum of infinitely many polynomials, if you want to think about it like this. So you would say, oh, this has infinite complexity. Well, not quite. Why? Because all the coefficients, they have algebraic relations, right? And so we should think of a new perspective. We don't think of the exponential function by itself as a polynomial, but we think of it as satisfying a differential equation where the right-hand side is a polynomial. The exponential function is still not enough in physics. Think about Feynman integrals. They are much more complicated functions. So we need to generalize this even more further. And so we need to first start with a very basic set. What is kind of the minimal conditions we have to impose on a function such that this is possible? Well, it shouldn't be too wild. And with very surprisingly, the amazing feature to make this possible comes from mathematical logic. And it's called o-minimality. So what does o-minimality mean? O-minimality introduces a notion of what is a tame set and a tame function. A function has then a tame graph as a set. It is a finiteness principle, so in the sense that the set can only have finitely many connected components. Okay? So the integers are out, but finite number of integers is a tame set. But this property really becomes strong if you impose that the collection of these tame sets is closed under the set theoretic operation. For example, the intersection of two tame sets should again be a tame set. And therefore, this collection we will now call an o-minimal structure. This is a tameness principle, and it is stronger than simple finiteness. Let me give you an example. Think about the infinite spiral. This has clearly just finitely many connected components, but it's not a tame set, because if you intersect it with a real line, which is a tame set, you get infinitely many discrete points, but infinitely many discrete points are never a tame set. Now, it's fair to say that currently in mathematics there's something going on which one might want to call a tameness revolution, because it has been found that if we discover that these structures are applicable in various fields of mathematics, we can derive really deep results with much more ease, or even new results. So this goes in algebraic geometry, arithmetic geometry, number theory. And just to give two examples, a long-standing conjecture, the André-Oort conjecture, has been proved recently, or it has been suggested at least, and the silver-pink conjectures for Hodge structures led to partial proofs. So there are several remarkable theorems and conjectures about finiteness in this field. Furthermore, only last year, a general mathematical framework was suggested where we actually keep track of this finiteness by this notion of complexity, okay? And this is now called sharp o-minimality. So there is the set of o-minimal structures, and the ones which have a notion of complexity is a subset. Now, I cannot give you an introduction to this subject because it's quite broad. However, I want to give you an example and kind of a key example class of where this is possible. And these are the so-called Pfaffian functions. So the basic idea is you start with some building block functions f1 to fr, and they satisfy differential equations. But not just any differential equations, they have some triangular form, but on the right-hand side of the differential equation, they are just polynomials. Okay, so that's the exponential function fits into this nicely. And then a Pfaffian function is again a polynomial in the coordinates and these building block functions. So we link everything to differential equations which are sufficiently nice. And now the key point is these Pfaffian functions are both tame and they have a notion of complexity. What's the notion of complexity? Well, we collect now the degree of all of these polynomials, and the format, this f, is now the number of variables plus the number of non-trivial functions. Very important to keep in mind. Because of this structure, the non-trivial functions appear in this format as a measure of complexity. And remarkably, you can now establish the same sort of bounds. Of course, these are different expressions for the number of zeros or for the volume and so on. So we need even more general settings in the following. You can always keep these Pfaffian setting in mind to follow up on the following discussion. Now, let's move to QFTs. I promised you we want to assign this to the functions appearing in the quantum field theory, and if I just take a canonically normalized scalar or number of scalar fields, then all the complexity sits in the scalar potential. So it's just the number of fields plus the degree of the polynomial if it is a polynomial, or if it's more general v, then you can think of it like as a Pfaffian function. Then it also f contains the number of non-trivial functions, these functions which satisfy differential equation. Again, what is the application? We can now find bounds on the number of vacua of the theory, or we can even constrain the slopes of the potentials. This generalizes to much broader classes of QFTs, and of course there are many questions to be asked about this, but I want to stay in the context of these potentials. As a small diversion, I need to stress that this framework is very powerful when it comes applying it to amplitudes, and that's why many of my recent papers are actually on amplitudes. And one can, for example, assign a complexity to amplitudes. These are very complicated functions, as we know, and tame geometry is just the right framework to study the singularity behavior, or asymptotics, or algebraic relations. Now, we have already made the first steps by showing that all Feynman amplitudes at finite loop order are tame functions, and now we are studying algebraic relations, and that this can be successful is indicated by the fact that, for example, for tree-level cosmological correlators, we got already quite far by using this complexity notion because they turn out to be Pfaffian functions. But it's a strings conference, so I want to apply these ideas to the strings landscape. So we go back now to a compactification which was discussed in the very first talk today. I want to consider string theory, M theory on some compact manifold, and think of the arising function now in this complexity spirit, okay? So the metric is now a polynomial in this non-trivial function, and the potential is a polynomial in these non-trivial functions. So concretely, we can look at flux compactifications of type 2V and F theory. So what are the scalar fields in these settings? They are the complex structure deformations of my compact manifold, and the metric K is determined by the second derivative of some logarithmic potential like this, while the scalar potential is determined from the flux superpotential in this form. The key point to notice here is that all the non-triviality in this expression sits in the periods, namely in these geometric integrals over a form on this manifold. And you should think of it like this. These periods determine these non-trivial functions f, and one has to use their derivatives. Furthermore, all we can choose are integers, right? For example, we can choose the fluxes to change my scalar potential. Okay, now we want to study the space of all of these possible configurations, and now I come back to finiteness. In fact, these finiteness conjectures, which I mentioned before, are implying that in fact, there should be only finitely many vacua satisfying this F-term condition and the Tadpole bound. This was an open problem for many, many years. But what we managed to do is we translated this problem into a clean mathematical statement, which then implies that if I impose the Tadpole bound, then there should be only finitely many connected components in the complex structure moduli space, even if I chose arbitrary fluxes. That's surprising because this condition still leads you to an infinite set of fluxes. What's the key complication is that what this means is the moduli space is non-compact. That means I need to control every path to every boundary at every possible Calabi-Yau manifold. And that seems like completely untractable if you do that like step by step. But due to this recent tameness revolution, we were able to use the tameness of the periods of these functions pi and some properties of the symmetry groups of the flux lattice to actually show that it's not only finite, this vacuum locus, but it's actually a tame set. So for example, it never contains these spirals. Now you might ask, how many are there? Well, I told you we have a notion of complexity, but unfortunately we are not yet there to obtain a new upper bound on these numbers. Okay? You have heard these numbers before, 10 to the 500. They were obtained from a flux density estimate. I don't know how much we should trust in these numbers. But if you work backwards, you actually can determine the expected complexity matching with the flux density expectation. So now I want to move to a second finiteness result, which in some sense is even more remarkable, right? Namely, I want to study the landscape of W equal to 0 vacua. And this means we have an additional constraint in order to this constraint. What does this mean? That means we can solve for the moduli, and then we have to solve the equation W equal to 0 over the integers, namely over these fluxes. So now we have a very complicated equation, which is often transcendental. Transcendental means that the function doesn't satisfy any polynomial relations. So a very non-polynomial equation, and this has to be additionally 0. These things have been studied in the past, but now we have an essentially complete picture because of this technology of the flux vacuum landscape for Calabi-Yau fourfolds. And we discovered that there is some remarkable arithmetic structure behind this W equal to 0 vacuum. At first, you might think there are just finitely many. That's a wild conjecture because you choose infinitely many fluxes. But the idea would be that the transcendentality is so high that these transcendental functions only finitely many times hit the integers. And this is actually the underlying reason why these two conjectures about the finiteness of rational CFTs or rank 2 attractors have been put forward. However, our setting is more general and has a much more exciting structure. So what is the structure behind this? There is a general pattern emerging in these moduli spaces, and it looks like this. Indeed, at a generic point of a generic Calabi-Yau manifold, so you're not allowed to take these manifolds or drop corrections as you like, really like the full periods. At a generic point in moduli space, the periods have extremely high complexity, and there are just finitely many flux vacua, unless they are on special loci, which are symmetry loci. On such symmetry loci, actually, the periods can reduce their complexity, become polynomials, algebraic functions, and the flux vacua, if I don't impose the tadpole bound, are dense. So now the picture of the moduli space is really that you have these symmetry loci inside them, and on these symmetry loci, there is a dense set of vacua if you don't impose the tadpole bound. But if the complexity on this period reduces on these loci, we can solve polynomial equations, and we can even do this exactly. And we did this for an example. This is like a genuine Calabi-Yau fourfold with 6 moduli. And you see here the periods, extremely transcendental functions, highly complex, generically transcendental. However, if you go to the symmetry locus, you just have one remaining modulus, and such a beautiful picture emerges. Remarkably, all of the vacua which you find in this manifold have a number theoretic meaning. Namely, these Calabi-Yau fourfolds contain what is called attractive K3 surfaces, so which have complex multiplication. And if we oppose the tadpole bound, some of these vacua are still okay, and these are now really genuine Calabi-Yau fourfold vacua, solved with including all the period corrections, no truncations, nothing. In fact, if you would truncate, you would not see this picture. So now let me conclude from these specific examples with some general final remarks. The curse and virtue of complexity. Our universe within string theory requires us to pick integer data to fix couplings to match observations, right? That's after modular stabilization, that's almost that's almost always what we have to do. For example, we can study the potential and ask what is it as a function of n after we fixed the moduli. Now, the typical argument goes like this. If we have very high complexity, very complicated function, we have many vacua, and this also follows from what I've discussed. And one of them has a small cosmological constant, right? That's the spirit sometimes. So a proposed realization is, for example, this Busso-Polchinski example. Okay? So indeed, we have these fluxes, and if we have sufficiently many, then we can make the cosmological constant small. So we have to increase the complexity, but the key point is this is a polynomial. It's a polynomial equation, and it has never been realized in string theory. Okay? My point, I think, which you can draw from the discussion which I described before, is that in string theory, actually, what happens is that the complexity increases because of non-trivial functions, because we should never fully ignore corrections. If we then impose v equal to 0 or even v equal to small, this can have very few solutions or no solutions because of the transcendental nature of the problem. So my suggestion is that we should put more emphasis on the number theoretic aspects in studying the landscape. Right? This is often done in amplitude literature, but it has not been done very much in studying these landscape questions. Furthermore, there is another competing effect if I increase complexity. Actually, increasing complexity can decrease the scale until which I can trust the theory. So the maximal cutoff goes down. So my conclusion is that there are a growing number of arguments that we need to have a revised approach to the landscape, maybe focusing more on these discrete aspects of the parameter space. And we should be more positive about the assessment about the predictive power of string theory. Because what is clear is that not everything is possible. So this leads me to my conclusion. I probably also am out of time. So I introduced a notion of tameness via o-minimality as a generalized finiteness property. I suggested that this is an extremely powerful tool, and we should use it in studying the landscape, but also in studying amplitudes. I mentioned that there is this new notion which has a notion of complexity, and I presented two finiteness results which are suggesting that there is kind of the option to either have the symmetry loci where you have a lot of vacua, or you are in a very transcendental situation where you have very few, very sparse set of vacua, much more sparse than previously expected. So I stress that one should pay more attention to these number theory aspects within studying the landscape. Thank you.
Questions? Clay.
One small question, like they have varied notions of complexity. Like, so for example, from quantum information side, in complexity is related to this information scrambling. So this complexity is any analog with that, or there's some connection with the quantum information measure of complexity, or are they very different from each other?
I don't think that, well, I cannot answer these questions fully, unfortunately. So in our paper, we discussed a little bit the connection to this quantum circuit complexity notion and so on. But I cannot answer this fully. We can discuss afterwards. But certainly this is a very fundamental notion of complexity, which purely kind of depends on like the logical information in a set or function. Okay. So my take on this is I want to work with this notion because there are very strong theorems using this.
Okay, thank you.
My question is about this notion of complexity for scattering amplitudes and cosmological correlators. Does it depend on which choice of kinematic variables you use to describe these quantities? For instance, in spinor-Hillisdy or twistor variables, these amplitudes take a much simpler form.
Yes, yes.
So does it
That's a very good point. So what I was not able to explain in this short time is that, of course, because it's such a fundamental notion, it means that it's actually not just one number. So you can always make a function more complex. So I can always add, multiply everything by 1, and then write 1 as cosine square plus sine square. So I introduced two very complex functions and to write something simple. So what this notion actually means is that there is a minimum of, it depends on the representation. The complexity depends on the representation of your function or your set. But the point is, for example, the exponential function, there is no representation of the exponential function which has the same complexity as a simple polynomial. So there is a minimum.
I see.
And there are two numbers, so the minimum is actually tricky. It could be that you have a representation where D is large and F is large. So there's sort of a duality between these two things.
See, thanks.
Hi, so I wanted to ask about the definition of complexity or tameness for QFT, or maybe more generally string theory. So most of your presentation was rooted in the Lagrangian of the theory. Mm-hmm. On the other hand, one of the main lessons of the last 30 years is not to put too much stock in a particular Lagrangian description. So I wonder if these ideas are well enough understood that you could understand the tameness of an abstract QFT, for instance.
Yeah, that's a very good point, and that's in our paper we actually also try to discuss kind of say that should we even think about the Lagrangian or should we think about the observables of the theory? So this framework is very general, and I applied it in this talk to something relatively simple, the scalar potential mostly, but you can also apply it to spaces of operators and so on. And people have done this. This is very technically hardcore mathematical literature, and it would be exciting to explore this, but it just has not been done. Of course, but the notion of complexity is relatively new. This has not been done for sure. Yeah.
Okay, one more. Come on.
Thanks for a nice talk. So towards the end of your talk, you hinted at a measure of complexity f being related to the number of light species or the inverse power of the species scale. So species scale is relatively well defined in quantum gravity. Its duality invariant may be not unrelated to what Clay was asking. So it does not depend on how you realize your Lagrangian. It's something invariant. So that would give you a handle if that's the case. So my question is it the way you're thinking? That is it possible that the species scale is with the inverse power related to your complexity, definition of complexity?
I don't know yet. My suspicion would be that within sharp o-minimality, there is one function, which is the CF, which I mentioned before, and there is a chance that this is related to the species scale. That would be extremely exciting. What is very nice to say is that it fits very much with many of the things we have looked at in the swampland program. So in fact, that like these infinite distance limits are infinite complexity limits, but then you have to switch to a different representation of the same theory where the complexity again falls between a certain bound. And why I use this, I just used it in the sense that minimally this complexity depends on the number of fields. So certainly there is a scaling of this type, but I left out the details in this last expressions. And it would be pretty spectacular, I would say, if indeed we can find the same dependence if we can fix these things here.
Okay, we should move to the next talk. Let's thank Thomas again. Okay, the next speaker is Gonzalo Torroba.
Okay, can you hear me? Okay, thanks. So thanks a lot for the invitation to speak here, and really special thanks to the organizers and particularly to the local organizers for the immense amount of work that's going into these unique strings. So my talk is going to be about time-like boundaries, holography, and cosmology, and in more detail related to the goal of understanding quantum gravity in space-times of positive cosmological constant. Okay? So recently, many developments have been converging towards this goal, and here I'm making a list with some references to have a better understanding of multitrace deformations, TTbar, and relation to cutoff holography, uplifts of ADS CFT to deSitter, progress in the understanding of time-like boundaries in general relativity, thermodynamics of cosmological horizons, and refined entropy counts, and also discovery of quantum mechanical models that are related to the system, to the deSitter, sorry, the role of the observers, algebras, and so on. Okay? And in particular, we are hearing many super interesting talks about these subjects in Strings 2025, so it's really nice to see how everything is getting connected. Okay? Now, in my talk, I'll follow a particular path through these developments, which is a path related to what we have been working on over the last few years. Okay, so first, I'm going to briefly review TTbar and its relation to ADS. Then I'll introduce the first key generalization, which is the so-called TTbar plus Lambda2, and explain how it relates to the deSitter 3. Then we'll use it to understand how to build the deSitter microstates and count deSitter entropy in 3 dimensions. 3 gravity dimensions. And finally, in step 4, we'll show how to put things together to build the local version of DS3 holography. And at the end of the talk, I'll argue how this can be upgraded to the realistic case, which is a 4-dimensional deSitter. Okay? And as I said, this is really work over now more than 6 years, so I really wanted to acknowledge my collaborators, so Gori Batra, Evan Coleman, Bruno De Luca, Victor Gorbenko, Edward Masenk, Vasu Shiam, Ronak Soni, Sung-Young Yan, and Eva Silverstein. And you see many of them here, so you can also ask them more questions or send comments. And also, before I continue, I wanted to highlight 2 main points. So first, for us, time-like boundaries are really, really crucial because they will allow us to introduce a well-defined boundary energy spectrum that will lead to the thermodynamics that we want. And in a nutshell, what we are going to produce is a prescription for a finite quantum Hamiltonian that formulates quantum gravity with a positive cosmological constant, both in 3D and in 4D. And the spectrum of this finite quantum Hamiltonian will produce the correct cosmic horizon entropy. So a picture of the spectrum is shown here in the right-hand side, and we'll understand how to get this spectrum by a series of deformations from the known ADS-CFT case. So that's basically where the talk is going. Okay? So let me begin with TTbar. So more than 20 years ago, Samolochikov discovered that in 1 + 1 dimensions, this so-called TTbar operator, which is a quadratic combination of T mu, has very special properties. In particular, it has exact dimension equal to 4. Okay? And many, many years after that, it was asked what happens if we try to perturb, say, one of our CFTs by TTbar. Now, in principle, we would think that we lose everything because this is an irrelevant operator, so it would break renormalizability. But surprisingly, it was realized that it's possible to define a simple trajectory towards the UV, so against DRG in some sense, that exhibits very special properties. And this trajectory is defined by this differential equation for the partition function. So lambda is the deformation parameter that allows to move along the trajectory. And essentially, at each step, we are adding to this partition function a piece of TTbar. Okay? If our theory at the beginning is a CFT, this differential equation can be transformed into an operator equation where in the left-hand side we get a scale variation which gives a trace of T mu, and in the right-hand side we get TTbar with this lambda coupling. So already by dimensional analysis, we see that this lambda has dimensions of length square, so it's irrelevant, as we said. And for us, the relevant case would be positive lambda. So from these works a few years ago, a key result was that if we put a CFT on a spatial circle, a circle of length L, then it's possible to compute non-perturbatively the deformed energy spectrum. Okay? So essentially, we are given some set of energy levels associated to the CFT that are determined by the standard formula. So the energy levels in the CFT are related to the conformal dimensions delta and the length of the circle and the center charge C. And then here in the left-hand side, you see the result for the non-perturbatively deformed energy levels. Okay? So this formula has something very important appearing, which is the square root. Notice that when lambda goes to 0, of course, one recovers the undeformed energy levels. We go back to the CFT. Okay? But the important point is that as we start increasing lambda, eventually this square root becomes complex. Okay? So for us, we'll use this to define a natural UV cutoff, which is that we'll truncate the spectrum at the energy level that makes this square root vanish. Okay? So basically, this is the natural UV cutoff defined by TTbar, and this will be an important point for us to deal with a finite quantum mechanics system with well-defined entropy. Now, sometime after that, it was realized by Margot, Messay, and Verlinde that actually performing a TTbar deformation of the CFT, if the CFT has a holographic dual, is dual on the ADS side to introducing a radial cutoff that creates a time-like boundary. Okay? So here, I'll explain that in very quickly. So let me write the 3D metric in this way. So there is some radial direction, and then these are the other two-dimensional coordinates. Time is contained here, and we introduce a radial cutoff, let me call it RC, where we fix the metric at some, with some Dirichlet boundary condition. And anticipating a bit in the next talk, so Dio will discuss different boundary conditions in GR. Here we'll be dealing with a Dirichlet case on the cylinder, which as far as we know is well defined. This Dirichlet wall here, this time-like wall, is characterized by an extrinsic curvature, which is roughly speaking the derivative of the metric with respect to the radial direction. Okay. Then an important point of ADS-CFT is that the stress tensor of the boundary theory is related to the quasi-local Brown-York stress tensor that one can compute in the bulk. And this quasi-local Brown-York stress tensor is directly determined by the extrinsic curvature via this formula that I'm showing here. Okay. So now the relation with TTbar is clear. We just impose the radial Einstein equation, which for pure gravity is the equation here. So it contains essentially the extrinsic curvature square and the negative cosmological constant. And we rewrite this radial Einstein equation by replacing k mu nu, the extrinsic curvature, in terms of t mu nu. That result gives precisely the trace flow equation that I showed here. Okay. So that's a quick way of establishing the connection between the TTbar deformation of the CFT and the appearance of a time-like boundary in ADS. Okay? And in particular, if one does this calculation in detail, one finds that the connection between the field theory parameter lambda in units of the circle radius, or the dimensionless TTbar coupling, is related to the gravitational couplings in this way. So here we have G Newton, the ADS length scale, and this is the typical length scale of the metric here. Okay? So that's a dictionary between the boundary and the gravity side. And moreover, the calculation of the dressed energy levels can also be mapped to the gravity side. We just put a black hole inside this Dirichlet wall and evaluate the quasi-local energy using this Balasura-Mannion-Krauss or Brown-York stress tensor. We find precisely the same structure that I was showing before. Okay? And so from the gravity side, it's also very clear what we are doing with our UV cutoff. Basically, the square root becoming complex corresponds to a black hole that doesn't fit inside the box, and we are not allowing that. Okay? Okay, so this is what I want to say about pure TTbar. Now I'll introduce the first generalization, and it's the so-called TTbar plus Lambda2 deformation. And the idea starts very simple. In any theory besides the universal T mu nu, you also have the identity. So we can think about deforming by both in a coordinated way. So the proposal is that the previous differential equation for TTbar is generalized by adding step-by-step here the identity operator. Notice that the identity operator is not added with an independent coupling, but the coupling here that appears is the same one that controls TTbar. So there is still a single coupling controlling both, so this is a coordinated flow. Okay. For convenience, I'm calling the constant here that appears 1 minus eta. Okay. And even though it's the identity operator, this turns out to have quite non-trivial nonlinear effects, precisely because at each step we have to recompute t, plug back, resolve, and so on. Okay. And we'll see examples of its effect. Okay. The key point for us is that this lambda2 is equally universal and also solvable as TTbar, and we'll see how it works out. And now we can ask the question, okay, what's the gravity dual of that? And just by repeating the previous exercise I showed with the Brown-York stress tensor, is in fact easy to show that this parameter eta that we have introduced here basically acts to change the bulk cosmological constant in this way. Okay? So basically taking eta equals to +1, which corresponds to having negative cosmological constant, that's the ADS case, and then lambda2 is 0, we recover pure TTbar. But for our purpose, we'll be interested in positive cosmological constant in the bulk, and so now we understand how to get it. We just need to choose eta equals -1. Okay, so that will correspond to DS3. So that's an important step for us because we already understand how to translate the change in cosmological constant in the bulk into a deformation in the boundary side by adding this lambda2. And now I'll come back to this calculation of the energy level so that I give you some flavor of how it goes to show that it's also exactly solvable in the lambda2 case. So how are these deformed energy levels computed? First, the previous differential equation that I showed is translated into a differential equation for the Hamiltonian. It's almost the same one that I showed before. Okay? And then this equation is evaluated on energy eigenstates. The factorization property of TTbar is used, and then the different components of the T mu nu are replaced. For example, the pressure here is, as usual, the variation of the energy with respect to the volume, and the T0x component is related to the angular momentum. So once these things are replaced into this equation, one gets a differential equation that can be solved for the energy levels, and the solution is of this form that I'm showing here. So that's the general solution to the differential equation that follows from here. Okay? This curly E is the dimensionless energy, so it's energy times length. Okay? So some things to highlight. This Y parameter is the TTbar coupling in dimensions of the circle radius. Okay? And then, so first one gets an integration constant because it's a first order differential equation. Here it's called C1. So in the previous slide, this integration constant was fixed because we required that when the TTbar coupling was going to 0, we recovered the CFT and the formed energies. Now, a new feature of Lambda2 is that we cannot just take this lambda that simply to 0 because if this eta is different from 1, you see that the Lambda2 coupling blows up when little lambda goes to 0. Okay, so that will play really an important role for us, which is how to define this integration constant and how to connect this to the CFT. Okay, but so that's the first feature. Okay, and the second feature I want to highlight is here you see eta, so eta appears in the square root. This is a very nonlinear effect I was anticipating before. And the third point is that in general there are two solutions to this differential equation. That's the origin of this plus and minus. And on the gravitational side, it turns out that these plus and minus are related to the fact that the extrinsic curvature is fluctuating and the manifold can be filled in one direction or in the other direction. So in general, they both contribute and they both have to be included. Okay? Okay, so this is the story with TTbar plus Lambda2 in a very, very brief summary. Now we want to understand how to use it to obtain the deSitter microstates and account for its entropy. Okay. So the generalization will be to start thinking about this two-step trajectory. As I said, we cannot just take the deformation parameter to 0 if we have Lambda2. So first we'll start from a CFT, we'll do a part with pure TTbar, and then we, at some value of the deformation parameter, we'll go along a different trajectory that contains Lambda2. So these are trajectories in field space, and just at this lambda naught, I'm turning on the Lambda2 deformation. Okay? And what we have to require is that energy, so continuity of energy levels here, okay? And this corresponds to a certain choice of C1. Here I'm giving an example, okay? But I'll get into more details soon with this. Essentially, what we would like to understand, so we already understand that on the gravity side, TTbar corresponds to having a time-like boundary. So we want to see whether we can use this idea with two steps to start with, say, a black hole in ADS where we know how to compute the entropy, and dress that into a region of DS that contains a cosmic horizon patch. Okay, that's kind of the gravitational idea. If we're able to translate that into a field theory deformation, then we would have an understanding of the deSitter microstates and what is responsible for the entropy. Okay, so essentially the intuition is if we want to understand the DS horizon of radius L, see how to patch it to an ADS black hole horizon of radius L, which in 3D gravity, this means a black hole around the Hawking page transition for ADS. So this is how the steps are done in more detail. So we start with a black hole at or above the Hawking page level. In CFT terms, this corresponds to a dimension of order C/6. Okay, this goes to the asymptotic boundary. Now, if we turn on TTbar, it starts, moving the time-like boundary towards the horizon. Okay, as we keep increasing y, this time-like boundary keeps moving, and eventually it gets like super close to the horizon. That corresponds to the square root vanishing. Okay, as we saw before. At that step, we turn on the Lambda2 deformation. Okay, and once we turn on the Lambda2 deformation, basically what as we already saw, this Lambda2 corresponds to changing the bulk cosmological constant, so it will reproduce the correct bulk geometry for the deSitter. We keep increasing y, that means we start moving in that direction, and in that way we obtain the cosmic horizon patch. Okay? I should clarify that cosmic horizon patch appears for one choice of the sign in front of the square root, is the plus sign, so it's the one that fills in the opposite direction to this one. Also the minus sign appears, and it turns out to give another state in the theory, which is the pole patch that appears here. So this is the gravitational intuition. What is happening in field theory terms is the following. We start from a CFT, we do a part of pure TTbar, and at some value of the dimensionless TTbar coupling y equals to 3 over pi squared c, we turn on Lambda2, and then we continue on the DS trajectory. This value of y naught is such that the highest energy level is this black hole at the Hawking phase transition or a primary state with dimension c/6. Okay? So at that step, we get a finite quantum mechanics system with a maximum energy and maximum entropy state. In fact, the entropy, we know very well how to compute. It follows from the Cardiff formula. And of course, it's the entropy that reproduces the black hole entropy by microstate count. Okay? So essentially, this two-step trajectory is dressing this band of energies, okay, and transforming it onto the ds side, where it's producing the ground state, as well as explaining the associated cosmic horizon entropy in terms of this microstate count. That's more or less by construction that it gives the right entropy. Okay, so now I'll give the proposal for this local DS3 holography. So far what we have done is to capture some universal features like the geometry and say the entropy associated to the horizon, but what we are lacking are important model-dependent details. For example, the structure of the energy levels, the details of the uplift from ADS to DS that so far we have done by hand, and in particular, the presence of local bulk matter excitations. It turns out that these 3 points are in fact related to the existence of bulk matter, okay? And it was understood by Tom Harman and collaborators that if we have a bulk matter field, say some field phi dual to an operator O, then the TTbar deformation needs to be generalized to include these double trace deformations, okay? And that's by doing the similar exercise to what I described with the Weidel-Einstein equation, okay? Now, one starts introducing these double trace deformations that are irrelevant and they introduce more and more UV ambiguities. We have to worry whether we have control over a complete theory at finite C. And in fact, our proposal is that we do, and we would like to give the following definition for what the complete theory at finite C is. Okay, so it's here depicted in this representation. So first we'll do a small step with just a pure TTbar deformation up to some small value yt, okay? And the main effect of this step is to produce a finite system because it will introduce a natural UV cutoff above which we are throwing the complex energies, okay? After we have that finite quantum mechanics system, we just continue with TTbar, and then these double trace deformations can be defined, okay? Because everything is finite, and I'll discuss that in the next and the other slide, okay? So they can be given an ambiguous meaning in this finite quantum mechanics system. And then since we are also including matter, this uplift that so far was done by hand, I was just touching lambda2 by hand, it will be resolved microscopically by the fields in the string landscape that connect ADS to DS, okay? And this was explored in detail, how this works out was explored in detail in a paper by Silverstein, okay? And so after we have changed the field from its ADS minimum to the DS minimum, this just continues with this lambda2 trajectory that I described before, okay? So these are the 4 steps enumerated in more detail. So the first step was to give you this finite part. And here I'm describing how the composite operators can be defined. So once we have in a finite system, we just have these sums and we do the appropriate subtractions, okay? And this is supposed to be done for all the matter fields, and in principle, this is done to match all the GR and EFT observers that we get in the local bulk. Okay, so there is some fine-tuning to be done there. I'll discuss that in one more slide. And then the next step, they follow as before. Now we have a well-defined meaning for these, double and multi-trace deformations. We have the uplift, okay? And in particular, the details of the uplift and the fields that enter there for DS4, they were discussed very nicely in Bruno's talk, so I refer you to his talk. And after that, we just continue along the lambda2, okay? So in summary, great. What this is giving is basically a finite quantum mechanics system with a type 1 algebra. It's able to describe local observables in GR plus effective field theory, and it produces an explanation for the generalized entropy. So, and now we are almost the end. So the last step is to understand how to upgrade to 4D holography, which is really what we want. So we want to understand the deSitter 4, okay? So there are new things in 4 dimensions. So of course, from the gravitational side, the new thing is that there are gravitons in 4D, and that's something that we have to deal with. And relatedly, in the 3D boundary dual, the generalization of TTbar is no longer observable, and of course, the stress tensor has more components than in 2D. Okay, So it's known that in D boundary dimensions, the generalization of TTbar is this so-called T-square operator that I'm showing here, and for us, D is equal to 3. And as I said, unlike what happens in 2D, this is no longer solvable. So we have a definition of, in order to make this solvable. And the definition we are calling here, the same type of differential equation I showed before. We are calling here the solvable deformation T squared sub S. And the logic is that we want to use this solvable part only to capture the entropically dominating states. Now, the entropically dominating states are spherically symmetric. So our ansatz is that we are just going to replace T mu here by the 0, 0 component, which is simply the energy density. And then for the spatial components, we'll only take a spherically symmetric pressure, which is derivative of the energy with respect to the volume. Okay, so basically, our answer for the solvable generalization of this T square is to replace a general T mu by this. And we'll deal with the extra components of T mu in just a moment. Lambda 3 is the same as before. And as was discovered by Tom and collaborators and Taylor, because of the curvature of the S2, there appears an extra term here related to the curvature and proportional basically to the Casimir energy of the CFT there, which, for example, for the M2 brane system would be n to the 3/2. Okay? But then once we plug this in here, we get a differential equation. It's solvable, and then the deformed energy levels can be computed non-perturbatively as before. So very similar to the expression in 2D. Again, eta appears non-linearly. There are two signs here, and then there is an integration constant to fix. Okay? And with this, our proposal for the full boundary dual to DS4 is very similar to what happened in DS3. And here's the picture. I'm getting to the end. Okay, so we start with the this first part of the trajectory is just doing pure T square with the solvable sector. This is with the goal of having just a finite quantum mechanics system. Okay, then we continue with pure T square solvable plus the matter contributions. The matter contributions now have the pieces left from T square, which are related to the graviton that appears in 4D, plus possibly bulk matter fields. Okay. Then we have the uplift, and then this continues, as I said, in the DS3 case. Okay, but it's the same idea. It's just that the new element is to use this solvable term in 4D. Okay, and what this does is starts from the spectrum of CFT, and here essentially by matching with a black hole at the Hawking page level that has the horizon of the DS we want, we get to a maximum energy and maximum entropy level, and that gets addressed to the deSitter where we are accounting for the cosmic horizon patch, the pole patch, and excitations in between. Okay? And to stress again, the logic is that basically this T square plus matter part is divided in two steps. First, the solvable step, which is capturing this most entropic energy band that explains the deSitter entropy, and then the model-dependent bulk matter part. And of course, that's the part where there is no free lunch. I mean, we expect in general many CFTs and many ADS and many DS vacua, all the model-dependent pieces going there. Okay? And in principle, being completely agnostic, what we can say about that part at this point is that this boundary theory has enough capacity to represent any observable that we get from GR plus EFT plus possibly low energy string theory. Okay, so in other words, we can just fine-tune all these composite operators and correlators in the deformed CFT to match to whatever we have in the GR side, basically because we have a huge Hilbert space and because GR is limited by 1/G Newton effects in its resolution. Of course, given a particular theory, there would be a lot of structure here, so this fine-tuning wouldn't be needed, but without saying that, I'm just saying here is that there is no abstraction to represent whatever comes from the bulk. Okay, so and this is basically the end of our proposal for the dual of DS4. So in summary, what we have done is we have defined a quantum mechanics system, and this quantum mechanics system is able to first describe the emergent DS radial geometry. Then it represents local biodynamics because it uses fine-tuning in its vast Hilbert space. And finally, it explains the generalized DS horizon entropy and thermodynamics in terms of a well-defined microstate count. Okay, thank you very much.
Questions?
forget for the moment the lambda deformation.
Yes.
Okay, when you calculate the entropy, you're just counting the number of states below the logarithm of the number of
Yeah,
states?
it's microcanonical entropy.
So in that, no, it's not microcanonical, it's infinite temperature. You give equal weight to all states.
Well, okay, this is an entropy calculated in an order one band around that. So it's, I have a finite quantum.
It's not just calculating the logarithm of the total number of states below the curve?
No. Even for the Cardi formula, it's the same as the Cardi calculation. So I can show it here.
What if you did just calculate the logarithm of the total number of states? Would that be the entropy?
It's very similar. It's very similar because the entropy is dominated by that band. It's very similar.
Yeah.
But here I'm just saying it's sufficient
Okay,
to have
good,
this order one band.
Now, does the lambda deformation change the entropy?
No.
Good. So my question is then, what does the lambda deformation do? In the sense, aren't you already in deSitter space by the time you pull the boundary in toward the...
Yeah, that step there. Yeah, from here to here. Yeah.
Aren't you already in deSitter space?
There, you're basically, you have the cosmic horizon patch bounded by a time-like boundary that is very close by.
Okay, so what is the point of the lambda physically? I mean,
Yeah, I mean, the lambda deformation is creating the correct geometry, if you want, from the bulk perspective.
But you already have a quantum mechanical system that...
it's deforming it so that macroscopically,
a maximally mixed density matrix, because it just...
Yeah, that one without Lambda2 does not have, its dual geometry is not DS, as far as I know. Or at least not from our perspective. Yeah.
Okay, I don't understand the second part of it, but...
Yep.
Yeah, right next to you there.
I mean, that you can already see from the equations of motion, right? If I don't turn on Lambda2, I'm just not producing the scale factor of deSitter. It's clear macroscopically, right? It's just
you
not...
pull the boundary back out to a point where it has very small area.
Yes.
How is it then sufficient to describe all of the entropy?
Yeah, so essentially, if you want, by choosing this value of y naught, as I said, you keep up to a maximum energy state, which is the one at the Hawking page level. The ones above that become complex and we are discarding. And the microcanonical entropy associated to this order one band is the same as the deSitter entropy. Yeah.
Another question? Juan? You bring the microphone to the back.
Yeah, so in duality, sometimes it's useful to focus on symmetries, right? So imagine you start from, let's say, a theory, so in your example for DS4, you start in an ADS theory, which is, let's say, the ABGIM theory, which has an SO6 symmetry.
Yes.
Now, by the time you get to deSitter, it looks like you continue to have the SO6 symmetry. But on the other hand, the deSitter vacua of the landscape, at least all the known ones don't have these.
No, indeed, yeah. That's part of the of this resolution. Like here, I was putting this lambda2 or lambda3 by hand. But if you have a complete, or once you have a complete model like this uplift from ADS3 to DS3 or ADS4 to DS4, you really have to put there. Sorry, let me get to the picture. Yeah, you really have to put there the fields that are responsible for the uplift. And for example, let's say you do ABGM, so you have ADS4 cross S7 not something, then that S7 will have to be turned into a hyperbolic manifold that will change the symmetries you're mentioning, okay, when you do the uplift. So in particular, the uplift will be responsible for modifying that, those model-dependent aspects. Yeah.
We should go to the next speaker. Let's thank Gonzalo again.
Thanks.
Hello? Yeah, it's fine.
Okay, the next speaker is Dionysios Anninos.
Okay, I'm delighted to be here, and I'd like to express my gratitude to the organizers for letting me share my work in this wonderful conference. I've learned a lot from many of you. I'd like to talk a little more broadly about boundaries in gravity. And in a sense, which one's the line? Yeah, I'd like to discuss some follow-up work to work that started for us in 2011, where we were trying to compute correlators along a whirl line in the static patch with Sean Hartnell and Diego Hoffman, and then a thickened version of that calculation with Tarek Anous, Irene Bredberg, and Jim Tseng. And the work is based with these excellent collaborators, and I'd like to highlight the driving force of this work, which is Chao Korn Manirand, who's truly excellent. Okay. So some context. We're accustomed to gravitational theories whose asymptotic boundary has a infinite spatial or null boundary. And this is virtuous in the sense that it provides us with good gravitational observables. It's a very useful thing to have, like an S matrix or boundary correlators. In certain circumstances, however, we're not afforded this luxury. And examples are quite relevant because they include spacetimes containing cosmological horizons or compact Cauchy surfaces. And we have to ask ourselves whether something can replace these observables or what to do. In those circumstances, and as far as I can tell, this question goes back to even the 50s, we may have to confront what people might call a more quasi-local description of the physics. From a more modern context, it's also desirable, as we heard, to bring in the ADS-CFT boundaries slightly inwards. This is something we may wish to understand and may help us think about more finite regions of space-time. And moreover, it appears a quasi-local description of the static patch decorated with some time-like feature may illuminate questions about the nature of the deSitter horizon, even if it's not the proper underlying complete framework. And this is an artist's impression of a whirl line and the possibility that it might end, to address one of Lenny's questions. Okay. So in this talk, I'll be broad. I won't offer any complete answers or frameworks, but I'll explore four-dimensional, mostly, general relativity in the presence of a finite size boundary in both Euclidean and Lorentzian signature and for general value of the cosmological constant. The work is open-ended, finicky, and ongoing, and I offer some sort of status report here. Okay, so gravitational world tubes. So let me discuss a little bit about the general relativity of these things. So you can view this as a little hole or tube in space-time, a little world tube, and you can be introspective or extrospective about it. So you could view it as something that looks outwards and measures features or even interacts with features of the ambient space, or you could view it inwards as filling in a region of space and trying to describe that feature, okay? And we'd view the boundary as some sort of data set or storage device that describes part of the regions we've excised. So we'll take a rather general view about this thing and try to understand it in a broad context. Now, what kind of data we may ask our friends in general relativity, what kind of data can we put on these hypersurfaces, these finite-sized world tubes, and whether the data generically has good properties or not? Can we develop the Einstein's equations and so forth? And a natural boundary to consider is the Dirichlet one, whereby we fix the induced metric along the whole time-like surface, along with the standard Choquet-Brouat type data along the initial value, a constant time space-like surface over here that intersects the time-like boundary. Now, for generic choices of this data, it's not obvious that this setup immediately works, and it may in fact suffer from existence or uniqueness issues, unlike the case of Yang-Mills or the Klein-Gordon field. Particularly near Minkowski or Rindler corner, there could be infinite sets of solutions that are not fixed by the Dirichlet boundary conditions. And also generic choices of gamma, which are not very specially selected, may fail to yield a filling at all. Now, this doesn't affect the previous talk, I should emphasize, because their very specific data was chosen, which has been proven to be consistent, at least at the linearized level. From the Euclidean point of view, one does not generically, the mathematical statement is that one does not generically have an elliptic problem for Dirichlet conditions, and this may affect the perturbative treatment of Euclidean pathing rules or the definition of heat kernels or functional determinants. This was first pointed out in a paper of Avramidi and Esposito in the late 80s, I think. Moreover, if you have a Euclidean boundary and you append it with some generic induced metric, in order for you to have a solution to the constraint equation projected on that hypersurface, the variation, say you're close to the flat metric, of the Ricci scalar, as shown in a nice paper of Anderson in 2008, has to have vanishing Ricci scalar. Nonetheless, I reemphasize, specific Dirichlet boundary conditions can and do display good properties. In light of these challenges, Michael Anderson and then Zhongzhang An and Anderson, for the Lorentzian case, proposed or conjectured instead to fix a slightly different collection of information along the tube, namely to release the conformal factor of this tube and instead fix the conformal class of the metric along gamma, along with the trace of the extrinsic curvature along gamma as well. So it's a slightly mixed problem. And they argued, and in some cases proved, that the existence and uniqueness problems are a little bit better. I should emphasize, though, this proposal was in 2021, and when you read this paper, you should, in between the lines, add that in addition to the data they propose and the data along the Cauchy surface, one has to be a little bit careful about specifying data in the corner where the time-like boundary intersects the space-like boundary. And in fact, unless one adds additional data at the corner, which has to do with the dynamic equation that governs the location of the surface, one may not be able to ensure uniqueness. And this was found in later papers, including a nice paper of Liu Santos and Toby Weissman. Now, given this alternative choice of data that you put on this hypersurface, you have to start asking some of the questions we tend to ask when we put gravity in a box as envisioned by York all over, because the Gibbons-Hawking-York term that gives rise to a good variational problem has to be modified, and this can affect some of the quantities we compute. For instance, the formal version of the Brown-York stress tensor, which is this thing over here, is a slightly modified version of the original one, which is manifestly traces from the get-go and conserved provided the boundary has conformal killing vector fields. In addition, bearing in mind this additional boundary data I discussed over here, T mu nu can receive contributions from these quantities as well. Okay? So we have a new notion of this boundary Brown-York stress tensor that we have to take into account. And to give you an example of how these boundary conditions can affect the kind of quantities we compute in Euclidean signature, imagine that you have lambda equals 0 general relativity with a boundary which is given by a two-sphere times a circle, which is the kind of boundary inside which we put the Euclidean black hole. What does the black hole thermodynamics formula for the entropy look like with respect to these boundary conditions? And given that we haven't fixed the volume of the boundary anymore, the black hole can actually be arbitrarily large inside this conformal wall, and we can take a different limit of the large black hole horizon entropy and get a very interesting looking formula for the entropy of a black hole inside this conformal box as a function of its temperature, namely to leading order at large temperature, now defined by the size of this S1, we get a term that is, for 4 space-time dimensions, quadratic in the temperature, with a prefactor, which is a dimensionless number, now built out of the new quantities of this theory, 1 over g Newton times the trace of the extrinsic curvature square. In ADS-CFT, this is the kind of quantity we would call n squared. And the square behavior in the temperature looks a lot like the behavior of a 3-dimensional conformal field theory at high temperature. So things change when you change these boundary conditions, and you can have formulas that look rather different and interesting. So now I'd like to discuss briefly the nature of linearized dynamics, gravity waves, whatnot, inside of these tubes, and see what new dynamical features they may encode or display. And so, for instance, let's start with whether or not there's spherically symmetric gravitational excitations. Typically, you'd say that there aren't because of the Birkhoff theorem, but here you can have a boundary mode which locally looks like a diffeomorphism, but governs a dynamical degree of freedom. And indeed, for these choice of boundary conditions, there exists a spherically symmetric boundary mode, which locally looks like a diffeomorphism, but obeys a type of equation, nonlinear equation of this nature, whose initial data has to be fixed to ensure a unique evolution. This is some sort of dynamic equation governing the spherically symmetric part of the brain. So here I should say the boundary metric is conformally equivalent to round 2 sphere times time, and I'm fixing the extrinsic curvature to be constant. Okay. So now we can ask, what about the linearized excitations of the gravitational field? What happens? Do they just bounce back? Do they grow? And you can decompose the modes in terms of SO3, angular momenta, M, L, and M. And if you have a Minkowskian filling, what you find is rather surprising, that actually in addition to the standard box-like normal modes that fill this tube, there's a collection of modes which exhibits complex frequencies. So the standard idea of filling it with normal modes that bounce back and forth appears to be disrupted. And this may suggest, provided that these modes grow nonlinearly, that the naive Minkowskian filling of this tube is no longer the standard Minkowski space, and we have to confront what the endpoint of these modes may be. Similarly, one can put these tubes inside of a deSitter universe to give you a different version of the calculation. And here you want to ask the question of what happens to these modes, say, as I vary the size of this tube inside of the static patch of deSitter. And I should say the role of K is to vary the size of this tube. And you could consider the case where the excitations are heading toward the cosmological horizon. And the nature of these complex modes over here, complex frequency modes, starts to depend on the trace of the extrinsic curvature as you vary it inwards or outwards. And there's a very natural limit you could imagine taken, where you take the surface of the tube to be almost located at the deSitter horizon, something like a stretch horizon limit. And in fact, in that limit, these growing modes become rather tame, and their behavior metamorphoses into a collection of modes that is somewhat reminiscent of shear and sound modes of a fluid dynamical system. Except for the fact that unlike previous discussions of these fluid-like modes, which had a negative bulk viscosity, by virtue of the tracelessness of the Brown-York stress tensor, these modes actually have a vanishing bulk viscosity, which is reminiscent of the kind of fluids people studied in ADS-CFT. Finally, let me make a comment about the thermodynamics of the deSitter horizon with respect to a clock that lives along this tube and measures the horizon. So this is paralleling some of the calculations of the previous talk, but with this choice of boundary conditions. And curiously here, the deSitter horizon has a feature that's not exhibited for Dirichlet conditions, which is that it can have a positive specific heat as a function of this temperature of the boundary clock. And you can write the deSitter entropy in 3 dimensions in a suggestive form, although I would be cautious with the interpretation, where the entropy takes the following form, governed by a parameter C, which is a function of the trace of the extrinsic curvature, which has monotonicity properties and grows as the wall shrinks to the whirlline limit and shrinks all the way to 0 as you push it towards the horizon. And you can do the analogous calculation for BTZ, and you find here the analogous quantity C, which, when the wall becomes the ADS boundary, goes to the Brown-Hanot central charge and then shrinks similarly toward the stretch horizon. So there's some interesting thermodynamic features. And how am I doing for time, Tom? Okay, good. So, and one can also do more exact calculations in 2-dimensional quantum gravity. But let me perhaps proceed now to the third part of the talk, which is, so far I discussed these tubes in Minkowski space and in deSitter space, and their dynamical properties. And now I'd like to discuss the more recent work where we're studying these walls in ADS-CFT. And the picture here is to start with the asymptotic boundary of ADS and ask what it means to bring it in slightly with respect to these boundary conditions. And so let me start by reminding you what the structure of asymptotically ADS4 is. At the infinite boundary, we have this type of expansion where the boundary lives at rho is equal to infinity, let me remind you. And the data is characterized by a metric, or rather a conformal metric at the boundary of ADS, and a transverse traceless tensor G3, which is typically associated to the boundary stress tensor of ADS CFT. One thing that we don't often emphasize is that all such configurations, or we don't emphasize it in this language anyways, is that all such configurations, if I calculate the trace of the extrinsic curvature at the boundary, is actually equal to 3 over L and insensitive to the particular state-dependent data. So one way to say what asymptotically ADS CFT configurations are is that they're configurations with a fixed conformal classal metric and a tuned value of trace K that happens to be 3 when the boundary is infinitely large. And so one can now imagine a situation where we start to tweak the value of trace K and see what happens as we move it around away from 3, yeah? As we've been doing in the previous examples. So what happens when we tune away from K is equal to 3 is that indeed, let's imagine again an S2 times time boundary, is that we move in the boundary slightly. But now we're moving it in with respect to these, while preserving the conformal structure of the metric on the surface, okay? And so now we can calculate, as before, the nature of the modes, the linearized modes that live in this slightly disturbed ADS wall where we brought it in a little bit. And what we find is that in addition to the collection of normal box-like modes that bounce around inside of ADS, we have a new set of modes that appears in the linearized spectrum whose dispersion relation to leading order when K is very close to 3, which remember is the ADS boundary, takes the following type of form. Omega is equal to square root of LL plus 1 minus 1, or in the planar case would look like a massless dispersion. So we have a new mode. And as we push, so here this is a plot for fixed angular momentum, and this is K going for 3 to larger values, which is pushing the boundary into ADS. So this is the Tower standard box-like mode. The red one is the new mode, which has a mass dispersion. And as we push the boundary inwards, there's for each angular momentum, a critical value of K for which this mode, which is real, acquires an imaginary part, and we retrieve the complex modes of Minkowski space. So the role of ADS appears to be to regulate some of these imaginary modes that I showed you over here, okay? Now, this is interesting because there's a new mode that comes to life when we bring in the ADS boundary with these boundary conditions. And let me make a remark about these new modes. The new modes are labeled entirely by the SO3 quantities. They don't have an analog of a bulk quantum number. So the data they encode is at most the boundary amount of degree of freedom, not a fully fledged bulk degree of freedom. And they can perturb the conformal factor of the boundary, which remember isn't fixed by boundary conditions. As K tends to 3 over L, you might wonder, why hadn't we seen these modes in ordinary ADS-CFT? What happens is that they parameterize in the strict limit a residual diffeomorphisms that preserves the Pfaffian-Graham data. But they're brought to life as the boundary goes in. And in planar ADS, one can do a similar analysis and find similar modes as well. What of the ADS-CFT Brown-York stress tensor? Here, there's a nice question, which is we typically calculate the stress tensor in ADS-CFT using the standard Gibbons-Hawking-York-Dirichlet boundary term. However, one can compute the Brown-York stress tensor for this modified term, and what one finds is that there's, to leading order near the ADS boundary, a term that diverges that we would ordinarily discard as an immaterial divergence in ADS-CFT, plus the term which is indeed equal to the Brown-York stress tensor. However, as we push K inwards, this term, which we ordinarily discard as immaterial divergence, starts to contribute to the energetics, it appears, which is a sort of interesting creature, without disrupting the tracelessness of the stress tensor. What about black hole thermodynamics? What can we say now about the high temperature limit of a black hole in ADS placed inside one of these conformal walls? What does it look like? Well, much like the other expressions I wrote down, you can calculate it in its most universal phase, which is the high temperature limit of this thing, and you find, again, an expression which goes quadratically in the temperature, like a hot 3D CFT would, except that the coefficient only matches the ADS-CFT prefactor, which we would call n squared, or something like that, in the ordinary ADS-CFT picture, now becomes a non-trivial function of k, which interpolates and monotonically decreases from the regime of the ADS boundary all the way to the expression that I wrote down in the earlier slide, where I had 1 over g Newton trace k squared. And so we have a new monotonic prefactor, dimensionless prefactor, that appears in the context of black hole thermodynamics that might be worth thinking about. And additionally, the new boundary mode can be added to the black hole and somehow dress it up and even alter its physical properties. Okay? So that's another feature. And so, how am I doing for time? 4? Okay, I'll give you a slightly prolonged outlook. So here's my outlook. This is, I think, a picture of Wheeler where the observer discovers the universe. Anyhow, here's a prolonged outlook. And I can only offer you imperfect thoughts because I don't understand this picture entirely. But I'm intrigued by the equations that come out of it. So I haven't answered for you microscopically what is the interpretation of this trace of the extrinsic curvature, which I feel is playing with the degrees of freedom, the underlying degrees of freedom, in an interesting way. It appears to be tied to the ultraviolet structure of the dual CFT in the sense that we're bringing in the boundary, and that tends to be associated with a cutoff. But I can't answer the question for you if you give me n equals 4 per Yang mill, what I'm doing to it to get this. The appearance of a massless dispersion relation in this new mode that I showed you when I brought in the ADS boundary is also evocative of the presence of something like conformal symmetry breaking, where you have a dilaton or some other general excitation which is massless that appears in the spectrum. This is naturally tied with the fact that though we're preserving the conformal structure of the metric, we have a dimensionful quantity parametrizing where we are, k. K has units 1 over length. And so we're tuning k. And the stiffness, in a sense, of this mode has to do with how far or close k is to 3 over L. Okay? Further imperfect thoughts, they're only going to get imperfecter. A concrete quantum object that we may wish to calculate, and we've done at very low orders in perturbation theory, is the partition function of Euclidean gravity, but now with a fixed conformal metric at the boundary and fixed trace k, where we might view these as additional sources for these new modes. This is an object that a priori we can calculate, and nothing precludes us from calculating it for arbitrary values of cosmological constant. So it's an interesting object that we can study in a broader set of theories than just negative lambda. It resembles, at least formally, a Legendre transform with respect to the ADS Dirichlet boundary volume form, because k is, in a sense, conjugate to the boundary volume form, and we're sort of doing a Legendre transform there. But due to these generic issues that I discussed, this can't be quite precise, because the Dirichlet problem is not completely well posed. And so I can't give you an explanation of that nature, at least in complete, with precision. As a future application, since I'm coming to the end of my talk, let me just say that these boundary conditions appear to yield interesting expressions for a variety of time-like surfaces, be it stretched horizons, whirl lines, thickened whirl lines, or near ADS boundaries. And what motivated a lot of this work, in fact, was coming from a different problem, which was trying to understand an object that appears naturally in quantum gravity for a positive cosmological constant, which is the partition function on a sphere. Because it's been argued by Gibbons and Hawking that that quantity calculates the deSitter entropy. However, being a sphere, it's rather featureless and esoteric. And one idea was perhaps if one excises a feature in this sphere and adds some extraneous data to it, it would be easier to understand. And so perhaps then these boundaries may help us split and join Euclidean path integrals in a more consistent way and dispel some of the puzzles, or illuminate at least the physical properties of this esoteric sphere path integral. And to give you a formula with the flavor that I'm discussing, you can take sort of an infilling and outfilling of the sphere, and the product at the saddle point level of these two partition functions, where I've removed a solid tube or solid torus in the sphere, yields an expression which is e to the deSitter entropy, or the leading order expression of the four-sphere path integral. It would be very nice to understand the nature of this formula to beyond the leading saddle point order. And since I have a minute, I have a special slide just to make the point more precise. At one loop, these expressions have very nice and very suggestive structure. And so I think we have a very clear-cut target to try to hit. Okay, 0 minutes. So is that a sphere or a 0? Okay, since my time is done, let me just thank you for yours. And yeah.
Questions? Yeah.
Thank you, Dio, for the very nice and stimulating talk. Something that confused me a little bit was that I would have thought in the quantum theory, which you didn't discuss that much, but perhaps towards the end. Let me just say it. In the quantum theory, one might have thought that to get a nice semi-classical space-time, it's not sufficient to fix either the metric or the extrinsic curvature, but you need to take a particular superposition over boundary conditions. And the reason I say this is in ADS, for instance, if you fix the conformal class of the metric at infinity and you solve for the radial Wheeler-DeWitt equation, you'll get a wave function at finite radius that has necessarily fluctuations in the metric and the extrinsic curvature. And if you look at the branch of the wave function that's an eigenstate of the metric at a particular radial value, that's not a nice semi-classical geometry in the bulk at all. So somehow, shouldn't that be important, that you can't really look at one or the other boundary condition, but you have to take a particular wave function, and we don't know how to fix that wave function ahead of time.
Just to be clear, this is a Euclidean expression, and at least in perturbation theory, I can imagine there being smooth solutions that I could calculate the functional, or I could calculate a functional determinant with respect to these boundary conditions. So are you saying even at the loop level? Just to understand the question. For instance, if you calculated this thing at one loop or in the perturbative expansion, would this issue arise?
I think so, but I'm not sure if it's let's say you look at the radial wave functional of the universe. So you fix the conformal class at infinity, and you just solve the radial Wheeler-DeWitt equation inside. That has fluctuations in both the metric and also the extrinsic curvature. And if you try to fix the metric, I mean, you'll get something, but that is not nice. It's not nice in the bulk. So one might have thought you need to take a very specific superposition that's in fact fixed by the boundary conditions at infinity.
Well, in that case, I look forward to running into that obstruction, but I haven't seen it yet. I can roughly hear you. But
for ADS3, you have these unstable boundary modes, but not for ADS4. Is that right? If I heard you earlier on, you had unstable boundary modes for ADS3, but not for ADS4. Is that a misunderstanding?
Yeah, so let me clarify. So the boundary modes are there for all cases, in all dimensions. And whether they're stable or not depends on specific choices of the extrinsic curvature and things like that at the boundary. The modes that, just to be clear, the modes that I was talking about, I'm not sure if you're referring to this plot over here.
Well, those omegas are all real, so I was interpreting that as being stable.
Up to this point.
Up to what?
Up to this point over here. So this is omega as a function of k. And so there's a critical value of k, after which I push the boundary and they acquire an imaginary part.
I'm assuming we want k very close to the critical value. Are you asserting that for every k less than the critical value, there's some unstable mode?
Well, the critical value depends on the angular momentum of the mode, and how large the angular momentum has to be. It goes like 1 over k minus 3.
Sorry, by the critical value, I meant k equals 3 over little l, as at the top of your slide.
Yeah, so if I move slightly away, essentially all modes are real valued.
That's what I was trying to say.
Yeah.
So you had what looks like a stable situation in ADS4, but do I understand correctly that the equivalent in ADS3 wasn't stable?
No, because in sorry, yeah, maybe I wasn't clear. I've separated the modes into a boundary mode, which is spherically symmetric, and bulk modes. ADS3 won't have the analog of these boundary bulk modes because there's no gravitons in ADS3. So the equation governing the boundary mode will be there for all of them, and one has to solve that equation, and that may or may not be unstable.
Well, supposing we want to always move the boundary in slightly, so we're near the critical value of k.
Yeah.
It looked like you have a stable setup in ADS4, whereas your frequencies were not real in ADS3. So
But I never plotted. Which frequencies are you referring? These are frequencies in Minkowski space, so 4-dimensional Minkowski space.
Sorry, but for large L, it would be the same.
No. So there's an interplay between how close you are to
I
k
see.
equal 3 and how large L is. Sorry, yeah.
So you do have a stable situation in ADS3?
The ADS boundary stabilizes these modes, but this is a 4-dimensional plot. In 3 dimensions, there's no analog of these bulk excitations.
Okay.
Thank you.
Sorry.
Yeah.
Is there one more question for Dionysios? Juan?
So, thank you very much for the nice talk. I was wondering what are the implications for the flat space holography?
Yeah.
Can you comment on that?
Okay, so I don't know. However, if you imagine trying to regularize null infinity by bringing in the null boundary to a slightly nearby time-like surface, perhaps some of the zero-mode degeneracies that appear in that case acquire more physical properties, like you can calculate different energies for them. And then you might be able to compute something like a degeneracy of BMS states or put them in some ensemble and do a Euclidean calculation even. That would be a fantastical idea of what could happen in this case. Yeah.
Could you give the microphone to Juan in the back? Juan, did you have a question?
Was there a question?
Yes.
Well, I guess talking to Herman, I guess I understood the answer to my question. But
No.
This extra mode sounds somewhat reminiscent to the Randall-Sundrum model, in the sense that there also you cut off the surface, you cut off ADS,
Yeah.
and the tension of the brane would be related to your extrinsic curvature.
Yeah.
And so one can understand these fluctuations as the motion of this brane.
Yeah.
But I realize it's not quite the same. Well, maybe you can comment more on this.
Well, I'd like to refer to Herman's answer for your question.
Okay.
I think it's a little different because you're putting slightly different boundary conditions.
Yeah, I agree. The conformal modes of the metric are not fixed in that case,
That's
but
right.
they are fixed in yours.
Yeah, thank you.
Okay, let's thank Dionysios again.
Thank you.
Okay, the next speaker is Sandip Trivedi.
Thank you. Okay, well, I'd like to begin by thanking the organizers for giving me the opportunity to give this talk. The title is JT Gravity in deSitter Space and its Extensions, and I'll report on 2 papers, one which we wrote some time ago with my now former students, Kanu Nanda and Sunil Sake. Kanu is at the Chennai Mathematical Institute as a postdoc now, and Sunil is at Kyoto University, and a more recent paper which came out during the conference, which is also with 2 of my current students, Indranil Dey and Akashdeep Roy, who are here along with Kanu and Sunil. Now, there are many other additional references. I won't be able to do justice to all of them, although I'll refer to some. But here I thought I would mention 3 papers which in particular were influential for us in thinking through the problem, and also refer to the work of Kristen Jensen and Kotler. Kristen already gave us a nice talk. Here are some of those references. And 2 more recent papers. These papers pointed out that in fact there are additional classical solutions after we make suitable identifications in deSitter space, which we did not include, and also elucidated some features about canonical quantization, which will be the topic of my talk today. So I highly recommend them to you, and I'll talk a little bit more at least about these papers as I go along. Okay, so here's the outline. Start with some introduction and motivation, discuss classical solutions, and then turn to canonical quantization. This will be the meat of the talk. And in the remaining time, just run through some extensions of JT theory. This is the content of the more recent paper. Path integral understanding for some of the additional states we'll find besides the no boundary state. And then some comments about a hologram as a matrix theory, and end with some conclusions. Okay. So Jakob-Teitelbaum theory, as many of you know, is a very simple theory of two-dimensional gravity. It has no propagating degrees of freedom, so you might say, why bother studying it? In the deSitter context, by way of motivation, as you all know, the moment you try to apply the laws of quantum mechanics to the universe as a whole, which is the domain of quantum cosmology, one is immediately faced with a host of conceptual issues. For example, what is the meaning and interpretation of the wave function? Who are observers and what are observables? And so on. And there is also the problem of time, which refers to the fact that a physical clock has to arise from degrees of freedom internal to the system. And then if you try and canonically quantize the system, which we'll try to do, a Hilbert space must be constructed at instances of this physical clock. And from that Hilbert space, and in terms of a norm you define, etc., you have to compute the expectation values of other degrees of freedom. Now, this is not the kind of issue we are faced with when we quantize normal systems, and we have to deal with it. And the hope is that these conceptual questions per se are not tied to UV divergences. So maybe we can try to understand them in some depth in lower dimensions, like 2 dimensions, and hope that that understanding will help us in more realistic dimensions. So that's the hope. Another hope comes from holography. These are very simple lower dimensional systems. We heard about deSitter 3 yesterday. Here we'll be in deSitter 2. And one might hope we can thoroughly understand them and see if and of what kind of a hologram they admit. And then hopefully that will help us too in higher dimensions. So much for motivation. Let me get going. Here is the action of JT theory. It's very simple, as I said. There's the 2D metric, and there is a scalar, which we call the dilaton. There's only one dimension-full parameter, lambda, which is positive for us. And we'll rescale it to be equal to 2. There's one dimensionless parameter, g Newton, which by rescaling the dilaton, because it sits in front of these terms, we can set equal to 1. And after we do that, the thing to remember is that the classical limit, g Newton goes to 0, will correspond to the dilaton going to infinity. There's also actually an additional term, which is a total derivative, which corresponds to the Euler density and is proportional to the Euler character. Its coefficient one should think of as being proportional to 1 over g Newton. When JT theory is obtained by dimensional reduction from higher dimensional space, then S0 is proportional to the higher dimensional gravitational entropy. And also the dilaton then is related to the radius of the internal space. The idea we'll explore is that the dilaton plays the role of the physical clock. Okay? And this is similar to what happens in inflation in our world, where the inflaton, which is also a scalar, plays that role. So this is the basic idea as we try and canonically quantize this theory. Okay, let's turn to classical solutions. This is global deSitter, and I've written it in these coordinates r and theta because the dilaton then is just proportional to r. D by d theta, as you can see, is a killing vector, and in global deSitter, it takes a total range 0 to 2 pi. So this is the Penrose diagram of global deSitter in 2 dimensions. It's a rectangle, not a square. And one can think of it like this. These dotted lines are lines of constant dilaton, and they also correspond to moving along the isometry direction. and you move along that direction up to a total range of 2 pi, and then identify the two ends. But because these dotted lines are isometry directions, you can also choose to do the identification where the range of theta is either less or more than 2 pi, and that gives you legitimate solutions where the aspect ratio of the rectangle can change. And you can put all these solutions together in the form of the following solutions. Now the metric has two parameters, m and a. I've rescaled things, so the dilaton is literally the radial coordinate r, the isometry direction, x, has a total range now 0 to 1. Okay, so there are two parameters worth of solutions. It's a two-dimensional phase space, a very simple theory. And the solutions I described so far correspond to this parameter m, which I loosely sometimes call the mass. It's not a mass, of course. We have compact spatial sections here, so not an ADM kind of mass at all, but just loosely, this parameter m is negative in the solutions I just described. Now, what happens if we take m to be positive? We continue to get solutions to the equations of motion, and they now correspond, after we identify the x coordinate, to orbifolds, but of a background which involves a black hole in deSitter space. So let me first start with the black hole, and then we'll turn to the orbifolding. So this is the Penrose diagram for a black hole in deSitter 2. Now there are two kinds of horizons. There are two cosmological horizons and two black hole horizons. The forward and past wedges, Milne wedges, outside the cosmological horizon are regions of space-time where the dilaton varies along a time-like direction, and it takes the value infinity in the far future and far past. And then the dilaton is also time-like inside the black hole horizons, now takes negative values in these two BH and white hole and black hole regions. And here I've drawn it so that the space-time extends till the dilaton becomes minus infinity. Okay, so this is the starting point. Now we can make identifications. We again take slices of constant dilaton, which again correspond to moving along the isometry direction shown in violet here, and we can take 2 points and identify them along all such slices. That now gives us an orbifold with a fixed point where the two cosmological horizons meet, the bifurcate point, and so you get a conical space-time with this orbifold singularity. I'll refer to this as a big bang, big crunch kind of space-time. When I give you explicit examples, they'll mostly refer to this branch. So you have a contracting universe, it hits the orbifold singularity, and then it goes into this expanding region. Now, since the dilaton was also time-like in the black hole, white hole region, you could also get a similar space-time, but now in that region with the dilaton being negative, and that's shown here. So you get another conical space-time. It's disconnected from this one, and it has a orbifold singularity as well. Okay, so these are the kind of solutions you get after you make these identifications. Now, what was pointed out in these papers was that actually, so before that, so now we have solutions with both the parameter m taking negative values, which were the generalizations of global deSitter. We can think of them as bouncing solutions, and those with m being bigger than 0. Okay, now what was pointed out in these recent papers very nicely was that there are in fact additional solutions. So let me quickly describe them. My analysis here will not apply to them, to those branches. So think of the extended Penrose diagram in deSitter space that contains an infinite set of alternating regions of the type I described, these cosmological regions and then black hole, white hole regions and so on, an infinite number of them. And one can now take, say, one cosmological and black hole region of the type we were doing, identify a point at the left edge with a point on the right edge after displacing it. And you can displace it, it turns out, by an arbitrary amount. So this gives one class of solutions, or you can take two such regions, alternate regions, and make identifications. And these are all allowed solutions. So this is a huge, huge class also, which is worth thinking about. And when I describe you'll see I'll make an assumption due to which the canonical quantization will not involve these kinds of spacetimes. So we have to extend it for them. Okay, and the technical reason is that now the spacetimes cannot be foliated by space-like hypersurfaces where the dilaton is constant. Okay, so the other thing to say, then we'll get going, is that this parameter m, the mass, is actually a conserved quantity, and when we go to the quantum theory also, it will play an important role. Last thing to say, and then we'll turn to canonical quantization, is that the wave function for the Hartle-Hawking state can be computed exactly in this theory because it can be obtained by analytically continuing from minus ADS2. That is anti-deSitter space, but with two time-like directions. That's a bit strange to have two time-like directions, but the path integral can indeed be made good sense of. And because the path integral in ADS2 is known to be exact due to earlier work, that means we know the Hartle-Hawking wave function also exactly. And that will help us a lot when we turn to canonical quantization. Okay, so usually you have an S2, but here you can also do it with a minus ADS2. Okay, let's turn to canonical quantization. I'll do very standard ADM quantization. N is the lapse function, N1 is the shift function. We'll work in a gauge where the lapse function is 1, the shift function is 0. And then we have their equations of motion, which are the Hamiltonian and momentum constraints, which need to be, and we have to, their equations of motion have to be set, we'll set h and p to 0 in the classical theory. It's also easy to check that these constraints close classically. Okay, so that's the classical setup. And now we turn to the quantum theory. If we are working in the basis of the dilaton and the metric, their conjugate momenta are functional derivatives. The wave function is actually a functional of phi and g1, which can vary along the spatial sections, and physical states must be annihilated by the Hamiltonian and momentum constraints. And so we would need to find such physical states to understand the canonically quantized quantum theory. However, this is not trivial because the constraints are well known to have ambiguities in the quantum theory. They have ordering ambiguities, but in addition, they actually also have the Hamiltonian constraint, which involves two functional derivatives, also has ultraviolet divergences. Of course, these are much more tame in 2 dimensions, but they are still present. And so you have to make sense of all these ambiguities before you can find what the physical states are in the theory. Now, how do we proceed? So the way we'll proceed is as follows. We will take slices, hypersurfaces where the dilaton takes constant value, and if the spacetime can be foliated by such hypersurfaces, then even if you hadn't chosen such a hypersurface to begin with, you can use the time reparameterization symmetry to move to such a hypersurface, and that doesn't change the value of the wave function. So we'll choose such hypersurfaces where the dilaton takes a constant value, and then the problem greatly simplifies because all the wave function can depend on now is just the one-dimensional geometry, but the spatial reparameterization invariance then tells us that it has to be some geometric feature of this one-dimensional geometry, which is only the length. So we've come down from a complicated functional to a very simple function now of just the dilaton, which is constant along each such slice, and the length. And that is the great simplification. But of course, we're not quite done yet because the Hamiltonian constraint still leads to a residual constraint on this wave function, a non-trivial Wheeler-DeWitt equation, and that Wheeler-DeWitt equation still suffers from ordering ambiguities and, in general, ambiguities. Thank you. So we have to try and fix it. And if you had just done mini-space, superspace quantization, which is a standard quantization, a standard approximation in this field, you would have got the following Wheeler-DeWitt equation. You can check that the Hartle-Hawking wave function does not satisfy this equation. In fact, since you know the Hartle-Hawking wave function exactly, that's a very good and strong guide. In fact, you need an additional term to be able to get an equation which the Hartle-Hawking wave function satisfies. This term is subdominant in the WKB limit, but it can be fixed from this requirement. And it's a reasonable requirement that the path integral gives us a gauge invariant state, and therefore reasonable to require that the form of the Wheeler-DeWitt equation should be such that the Hartle-Hawking wave function satisfies it. So now we have a Wheeler-DeWitt equation we can trust, and we can go ahead and write down all the physical states in this rather simple theory. And here they are. Two of them look like this. Here the value, a parameter m is just a parameter now for now in the solution. The two solutions correspond to e to the minus il with the square root or plus il. And when you think about the momenta, resulting values of the momenta, this corresponds to an expanding universe, and the other choice corresponds to a contracting universe. M can take any value. The Wheeler-DeWitt equation was linear, so you can in general sum over all values of m with arbitrary coefficients. And these are the most general solutions to this very simple Wheeler-DeWitt equation in this theory. Okay, and you see that there are infinite number of them, one for each value of m in both the expanding and the contracting branches. Okay, and m actually turns out to be the eigenvalue of an operator in the quantum theory. Now, we're not quite done understanding the quantum theory because we still have to obtain a Hilbert space of states, and that requires us to define a norm. And the way we'll do it, as I said, is to construct a Hilbert space at constant values of the dilaton. And it turns out, because this Wheeler-DeWitt equation is so close to a Klein-Gordon equation, in fact, after some small change of variables, it can be put more or less in the Klein-Gordon form. There's a natural norm that suggests itself, which is very close to a Klein-Gordon norm. So that's the norm we'll take. But we are still not done, because if we want to ensure that the norm is conserved, let's say we are working now in a single universe sector and we want to see if you can canonically quantize just in this sector, ensure that the norm is conserved. You've got to ensure there's no leakage of probability. And the stringent constraint comes from the lower end, where the length of the universe goes to 0, okay, because the length cannot get negative. So you've got to ensure no leakage of probability. That gives rise to a condition. And that condition, it turns out, can be quite easily solved by imposing the analog of Neumann boundary conditions. This is the line L equal to 0. And the reason it's not dl psi equal to 0 is because these L and phi are like null coordinates, okay? So after you do this, you have no leakage of flux, a well-defined norm, and now you have a good quantum theory, and you can explore what are the resulting states. Now, this condition cuts down the number of physical states, but you started with an infinite number. It cuts down the number of states by half. It's like a Neumann condition. You're still left with an infinite number of states. So this is the quantum theory. I should say one thing. I'm using the word norm, but it's not actually positive definite. It won't surprise you because it's like a Klein-Gordon norm. So depending on what your wave function was, you have to choose one sign or another to make it positive. Okay, so that is one thing. But anyway, you have a conserved quote within quotes norm. Now, let's see. Now you can try to understand some of the resulting physics. It's kind of interesting. If you take a universe which in the far future is nice and classical, a tight Gaussian wave packet, and run it back so the dilaton decreases, it goes towards the orbifold, you find it goes through in the quantum theory the orbifold and expands back out into the far past as another nice, smooth, classical universe. Okay, so in this very toy model of the Big Bang, you have time before the Big Bang. Okay, now I'll be a little quick. I wasn't very clear about the range that the dilaton should take. If you dimensionally reduce, the dilaton can't get too negative. But here, let's just consider the 2D theory in its own right and ask, what constraints do arise for the range of the dilaton? It turns out, for example, if you say, I'm not going to allow the dilaton to get negative, it's too restrictive, there's no non-trivial solution there with the Neumann boundary condition. And in fact, it turns out the wave function you get if you just impose the Neumann boundary condition is perfectly analytical across phi equal to 0. So you can just extend the wave function, taking the range of the dilaton to be now from minus infinity to infinity, okay, in this 2D theory. When you do that, what happens is, let's say you started again with a component in the far future. You have the component I mentioned in the Big Bang, Big Crunch branch in the past, but you also now, it turns out, the wave function has two components in the black hole, white hole regions. You can think of this as follows, that the wave function initially in, say, the expanding branch tunnels out through classically disallowed configurations into this other space-time. Okay, and so that's what comes out, and you can explore such kinds of solutions. Now I'm going to move on, other than to say the Hilbert space I constructed is not unique, and you'll see this again when we talk about holography. The set of solutions is well defined, but you can associate different Hilbert spaces. Some of the choices are discussed in this very nice paper. They correspond to different kinds of norms tied to group invariance. You could also explore choosing a different kind of clock. Besides the dilaton, you could choose slices of constant extrinsic curvature, and that gives you and the resulting quantum theory is different, and it gives you a sense of how things can differ depending on how you solve the problem of time. But I have a problem of time, so I'm not going to go into this right now. Okay, now what is the path integral understanding of these other states we have found? The Hartle-Hawking state is very well understood as a no-boundary state. Can we understand these other states? And there's a limited understanding we have for some of these other states. And the idea is as follows. Let's say we could deform JT theory by changing the potential, the dilaton potential, so that asymptotically, in the classical region, where the dilaton becomes very big, that potential goes to the JT potential. Now we construct the no boundary state in this deformed theory, and that should become some state in the original JT theory, but it won't be the Hartle-Hawking state of the JT theory. And in fact, you can play with this idea. This is an example of a more general idea which was discussed in this very nice paper of Chakravarti, Gode, Paul, and Surat Raju of mapping different states to different theories in deSitter. You can try out that idea by adding exponential corrections to the potential, and indeed you get other states in JT theory with different coefficient functions. Now, in fact, this idea of deforming JT theory can be explored in canonical quantization as well and taken quite far. What you can do is, again, work with a different dilaton potential, and it turns out to be, for a large class of potentials, that this canonical quantization I described for JT theory can be extended quite easily. You can completely quantize the theory, understand the Hilbert space, and so on. And what happens is that, in fact, the states, if I give you a moment to look at it, the states become states in the original JT theory because the U of phi becomes the potential of JT theory. So in the far future, you have states in these deformed theories which look like states in JT theory. But of course, when you go back in time, then the two theories are different. And now you can often have, instead of an orbifold singularity, a genuine curvature singularity, and explore what the quantum theory does if you're going to hit those singularities in the course of the resulting cosmology. So there's actually a huge class of interesting two-dimensional cosmologies that you get to play with in this way, where you've understood the quantum theory quite precisely, and we do that in our recent paper. Okay, I'm going to end with just 3 or 4 comments. These pertain to holography, and now I'm only going to refer to this big bang, big crunch branch with the dilaton going to infinity at both ends and m being positive. And the Hartle-Hawking state can be understood as the expectation value of the partition function of, in fact, the double scale matrix theory of Sath-Schenker-Stanford, which of course is connected to ADS, but now at an imaginary temperature. And we heard about such connections also in Kristen's talk. It's probably not surprising because the contour which gives rise to the Hartle-Hawking state is related to ADS with 2 negative time directions. Perhaps not surprising that this happens. At any rate, this is something you can explicitly check. This prefactor tells you you're in the expanding branch. Now, what about the other states we found? Okay, it turns out they can all be mapped into the same matrix theory, except instead of that trace you had of e to the minus beta m with imaginary beta, you have the trace of a more general function inserted inside. Okay, one function worth. We had one function worth of states corresponding to that coefficient function, and similarly, you have a one function worth here. So in other words, you can map every state, a state with a mass parameter m, which I told you about, can be mapped to an eigenstate in the matrix theory corresponding to the eigenvalue E of the matrix taking value m. This means that, in fact, you have another Hilbert space now for the bulk, which arises from the Hilbert space of the boundary theory. You know, the boundary theory is a very simple matrix. There is a natural inner product you can associate, thinking of that matrix as an operator, if you like, or just as a matrix. That becomes an acceptable Hilbert space for the bulk, and the states, all these states can be taken to be as acceptable states in the resulting Hilbert space. So when you work it all out, this is the nature of the norm you get. It's different from the one I wrote earlier. It's positive definite. The other one was not. And also states we threw out are in fact included here. And that might not be surprising because matrix theory actually allows you to change the number, allows for topology change. So there's no reason why the norm in a single universe sector would need to be conserved in terms of this norm or inner product that comes out of matrix theory. So this tells you can have different kinds of norms you can associate. Now, we need to develop the path integral interpretation for these other states much better to check whether the multi-boundary contributions can be computed in the bulk and can agree with these corresponding computations in the matrix theory, but at some level this works out. At a leading order, sort of one boundary, it works out well. Okay, last thing, and then I'll stop. JT theory is therefore now dual to the double scale matrix theory, but just suppose for a moment this duality could be extended to large but finite rank, and this requires more work, but just suppose that could happen, then something very nice happens, because L, the rank now, is the topology counting parameter in matrix theory for usual large n reasons. E to the S0 is the topology counting parameter in JT theory because S0 multiplied the Euler character, so they are equal. But L is also the number of states in the matrix theory, which because of this one-to-one identification I was telling you about, is also the number of states in the bulk. And E to the S0 is also the gravitational entropy, at least as seen from the higher dimensional theory. So we have a very nice sort of possibility that in fact the number of states in the bulk equals the gravitational entropy, which equals also the number of states in the boundary theory. Okay, now there's much more to do to just take the idea of holography to its logical completion and really test it. And then the fact that there should be an extension which holds at finite L requires even more work, but it's a very interesting possibility that a hologram at scri plus and minus future and past space-like infinity can account for the deSitter entropy. Okay, so I'm going to end there just quickly with conclusions that canonical quantization revealed an infinite number of states, and this suggests at least that states other than the Hartle-Hawking state should be given more consideration in cosmology. A better path integral understanding of these states would be very helpful. We're trying to work towards that. And of course, holography needs to be understood better, and we need to go beyond 2 dimensions. There is always a feeling that what we are finding is too closely tied to 2 dimensions. The matrix theory was the same, because the path integral could be computed by analytic continuation and so on. If some of this holds in some way in higher dimensions, then we'll feel much more confident. So I end with that, except to say thank you, shukran in Arabic, and shukriya in Hindi. I hope they sound similar to you, because after all, the West Coast, as we call it, and Mumbai in particular, is close to Abu Dhabi. And so look forward to many more interactions in the future. Thank you.
Okay, we're a bit over time, but we can take approximately 1 question.
Sorry. I think lunch.
Eva?
Okay.
Right there.
Thanks for the really interesting talk. I want to sort of ask you something about your last comment, and you're kind of maybe the unique individual I can ask about this, which is in higher dimensions, one of the things we do know is that deSitter is metastable. And that's related to what you just said. It's not an analytic continuation of ADS times S. It's an uplift, which introduces complications, but they're tractable. Is there any sense in which this 2D model, has some avatar of that, or is it very, very different in this regard?
Yeah, that's an interesting question indeed. And when you play with these dilaton potentials, you can try to set up examples like that. And we have explored them a little bit, but not fully. I would say I don't have a concrete answer. The simplest examples, because 2D is different from higher D, don't give rise to tunneling or decay, even though you might naively think they do. So if we added more stuff, I think we could certainly do it, but I'm not sure that happens in the simplest.
Okay, sorry, another request to add is combine all the talks in the session to put in a time-like boundary in this. You get something interesting.
Okay, okay.
Has that been done, or?
No, not that I know of. Not that I know of. But yeah, one could try some lower dimensional version of TTbar and then try to see that. I haven't done that. Thank you.
Okay, let's stop here and thanks Sandip again.